I'll do my best to wake you up a little bit. So I mentioned already that I've been in the MBSE field for quite some time, about since 2008. And there have been several occasions where I gave talks in the past, and I remember one in particular, which was in Singapore some years ago, where the organizer of the conference sent out an email the day before I gave the talk that every speaker had to wear a shirt. Right? Okay, well, that's a new requirement. No, I have to wear a shirt. I have to dig out the shirt. I don't like shirts very much. So then I started the talk, and since I don't like shirts very much, I took off the shirt during the talk, and nothing happened. Nobody cared if this requirement was met or not. So, and I used this story in other talks the years after as a sales pitch for MBSE, because this is one of the problems we want to solve. No? We have some requirement, we change something somewhere, and we would like to know that something has changed. But actually at that time I didn't know really what I was talking about. I had some ideas, some vague idea, but it only evolved over the last years. It became more concrete. I think now I know a little bit better what I'm talking about, and that's also the focus of this talk. Originally, or the main title is about system engineering products with an executable, using executable models in a model-based engineering environment, which sounds very abstract. The actual core of this presentation is about using executable models for analysis and verification of requirements. So there's a quick outline. I will talk a little bit about the current state of practice and the need for MBSE, and I'm still convinced we need it. I will quickly give an overview of system development process and how it falls into MBSE. I will show an application to a production system with a production model for the 30-meter telescope that I'm working on, and I will present infrastructure for a systems modeling environment that we have been developing at the Czech Propulsion Lab, and then a summary. So about me, there's not much to say. I spend a lot of time on telescopes. At the moment at JPL, I work as the lead systems engineer for the whole lab-wide mission engineering environment, model-based environment. I work on basically the software infrastructure provided to the system engineers and domain engineers. And I spend the other half of my time on a system engineer on the Europa Clipper project and on the 30-meter telescope as a system engineer. So currently, and that has been going on for quite some years, on the discipline side, we have models already everywhere. No, they're all over the place for CAD, for FEA, we have MATLAB and all this other stuff. But still there's a lot of documents around, a lot of artifacts, which are very often disconnected. So they are very often also at system engineering level. So what we want to do, that we need MBSEs to tie in the system level models into the existing models, so to integrate them in terms of information, tooling, and so on, and to provide a method. So we need two things: we need a method and we need a tooling environment. And I believe we are in a good way on both sides in this case. So the typical problem is that you have a lot of people that produce a lot of information, which is often captured in documents, and you have this typical situation where you have a lot of implicit dependencies between these documents. When you look at two documents, you have two numbers in these documents, and you wonder, okay, are these the same numbers? Are these numbers being produced with the same tool, with which version of the tool, with which version of the model, with which version of the data? Have they been verified? What are these numbers? That happens very often. If you look at the traditional V model of engineering, you have all the definition on the left leg and the verification on the right leg. And this model typically implies some waterfall, which is one problem, so there is no iteration. And the other problem is that the verification, at least in the traditional approach, happens only on the right leg. Well, there's not much of verification on the left one. So from a system engineering process point of view, as it's, for example, defined by the ISO 15288 standard. You will typically start as a system engineer to look at the stakeholder needs, to develop the requirements from them. You will come up with some architectural design based on some objective measures and requirements and functions. You will do some trades and also some technical evaluation to come up with some logical architecture, synthesize this logical architecture or functional architecture into some physical architecture. Now, that happens in one way or the other. It can be model-based, it can be document-based, but it happens. It can be only in your head, documented, not documented, and so on. So what we want to have more control over how this happens. So there, MBSE comes into view. Just as a reminder, MBSE is the application, formalized application of various modeling techniques, which should support the whole life cycle of system engineering. So analysis, verification, validation, design, architecture, and so on. Typically, MBSE people use some systems modeling language. The popular one is SysML with all its problems it has, but it's still the best available at the moment. It's often used with a method. If it's not used with a method, usually it ends up in a big mess. So the one that I've been using and my team has been using for some time is the object-oriented system engineering method, ESEM, which was initially developed by Sandy Friedenthal at Lockheed Martin. And you can map this ESEM onto the ISO system engineering process that I showed before. So at JPL we have developed, or we have been developing an update of this B model. So you have still the legs, the left and the right one, but then in the middle you introduce all kinds of models for all these levels. So you have all the requirements flow down on one leg, and you have the verification system VLB on the other one. But at every level you have some kind of model. So what I will talk about in the next minutes is basically all the models around project requirements, system requirements, and the architecture and design at system level. So where you see the red circle. Now the ESEM object-oriented system engineering method is an iterative process and incremental and recursive. It focuses mainly on the definition of the requirements and architecture and the specification of the elements, the conceptual and realization or physical, whatever you want like to call it. And this is also where we inject the executability. So this is the ESEM process. You start with analyzing stakeholder needs. You analyze the system requirements with some artifacts of system context, system scenarios. You define a logical architecture, and you synthesize your physical architecture, and you do some trades in between. Wherever you see the red circles, we leverage this object-oriented method with executability, which means we're using executable models with well-defined semantics, so we can have better analysis of the model itself, of the design itself, with respect to its requirements, and I will show how that works. So for the system analysis, we want to assess quantitatively the system architecture and design, and to provide some method for rigorous approach for decision making. So we'll do all the technical, at the moment, technical analysis using model and verify them against the requirements that we have. So in this case, we will have a conceptual model, a conceptual design, and a realization design, and we will verify if the design meets the requirements that we have. So now today, and for the last year's SysML models in particular, the focus was on the syntax and the notation, so it was a little better Visio, Still at the end, the diagrams were mostly consistent, but there was not so much emphasis on semantics. Now moving to executable models, the picture changes completely. So you have a different modeling experience, because suddenly you have to be more rigorous and care about the things to make it executable, to simulate, to analyze, to have well-defined semantics. So, and in particular, on the side of behavior. So most of the things I will show today are around the behavioral description of your system architecture, embedded in some structure. So the proposed approach is to use executable models in order to enhance the understanding of our system, to verify the requirements, and to increase the precision. And we introduce an engineering method which we call ESEM, which is the executable system engineering method, which augments the OSEM method by applying various patterns which are documented in this paper and in other papers. I will not go in this talk in all the details, because there are a lot of details to construct how to construct such a model, how to validate it, how to execute it, and so on. So I will show the highlights, and then if you are still interested, then you can look at the papers or talk to me for further details. So ESEM introduces a number of analysis patterns to construct a model and carry out structural, behavioral, and parametric analysis. And it also enables the integration of customer and supplier models, which in the TMT case is also relevant. So very quickly about the TMT and the context in which this happens. So JPL delivers, acts as a supplier to the TMT project. The subsystem I'm working on is the alignment and phasing system, which is delivered to the TMT project. And the APS is responsible for measuring the waveform quality. So the objectives for the TMT are to have an executable system model to capture the requirements, the operation scenarios, the operation use cases, to capture the composition of the system functionally and physically, the relations between the subsystems, and the interfaces. Right? And we have to analyze the system design with respect to some requirements, which are the requirements on mass, power consumption, and duration. So certain scenarios are limited in time, like segment exchange should not take more than 2 hours, and we have to demonstrate that our functional design meets this requirement. Several documents are produced out of the model directly, so they are auto-generated documents, and they are the requirements flow down, the operation scenarios, the design description, the detailed design description, and the ICDs, the interface control documents. The other goal was to use as much as possible vanilla SysML, standard languages, and to avoid custom software development. So we can use off-the-shelf tools without scripting, plugins, or whatever. So really off-the-shelf things. So what we do is to capture the operational scenarios with their estimated time, so the estimation that we consider adequate, and you would have something like a 2-hour requirement for the post-segment exchange alignment, and the current best estimate that comes out of our model is 1 hour and 19 minutes. And we verify this requirement automatically within our process. Then we also capture the characterizations of the components in terms of power and mass in order to verify, do power and mass roll-ups, static and dynamic, in order to verify the requirements on those constraints. As part of the process of behavioral and structural modeling, we identify all the involved subsystems, so we identify also the interfaces between those subsystems, so which requirements are on our side, which requirements are on the other side. We analyze the associated scenarios, so like the use case scenarios, and we automatically verify at the end the system requirements. And I will show you some video on how that works. and we derive then the requirements for the TMT subsystems. And that also helps to develop and refine the timing requirements and to find out the internal external interface. I'm too heavy, obviously. So one typical scenario is that we have some requirement on time and power, for example. So like 2 hours, and we have a certain exposure time and some power maximum power consumption and a number of motors. So a typical change scenario would be if you change on either side something. So either you change the requirement, you will still want to verify if the design holds against those requirements, or you change something on the design side and want to see if that still meets the requirements. So what happens is if this requirement changes, we have the TMT project uses the DORS database to manage the requirements, DORS 9 database. We import periodically requirements into our system level model in Magic Draw. We formalize these requirements into system level constraints. So they're not just text, but all the things that are textually captured in the textual requirement are converted into some model elements, so we can trace and verify and flow them down in our model. We then, so that happens here, we then do an analysis of our conceptual and or the realization design. So we run a certain scenario, get the total time, or we do a dynamic power rollup for a certain operational scenario and determine the peak power. And in the end, we verify automatically this requirement, the result against the requirement, and the tool will tell us if it passes or fails. And all this will be in the end generated into the documentation. So we have the documentation of the design, the analysis, and we know, and all this is under version control, obviously, so we know for each document with which version it has been produced, and if the design which is documented, captured in the document, meets the requirements which is in this document. So all this is used for operational concept document requirements, ICD, and design, detailed design. So what that leads you to is that you have a lot of information floating around from different domains. So there's the part of your system architecture, you have requirements, you have application lifecycle models, you have PLMs, you have the mechanical, the electronic power project management. All over the place there is some information. So in the end you will have some information, some graph which defines the dependencies between your information. At the moment we focus, in this presentation focuses on the red circle, so the relations between the nodes of simulation, system architecture, system design, and requirements. The infrastructure that the building encompasses all the domains you see up there on the screen. Note also that there's also possible relationships between the ALM simulation, MCAD, and ALM node level. So there's a big graph that you have to manage, a big graph of information that you have to manage. So here I show, I will start with a video which takes a couple of minutes, which will show several things. It will show part of our infrastructure, which is a web-based interface to our model management system, which is called MMS. So it's a lightweight web client which allows you to view your model as a document. So basically this is the document that in the end you get as a PDF. But at the same time it allows you to change everything, but a lot of things in this document-based view. So like values, text obviously, but also values. And they go, they are directly changed in our model as well. So that the user doesn't know that there's a model behind. The user sees some numbers, some information, changes it to be propagated to the repositories that we have synchronized, and we can run analysis on that. The other, so that's the lightweight one. You will see another tool, which is Magic Draw, as the rich client platform that we use for system level modeling. There at the moment we carry out the analysis. but we want to migrate that to the server side. So there's two things. We have some server, some repository, and two clients, a rich client, Magic Draw, and a lightweight client, which is the so-called view editor on the web. I hope this starts. So what you see is like a tree of so that's one document, like all the use cases. You see like requirements values, these are all the requirements that we have, which are generated from the model, different diagrams. You see the structure of the document on the left-hand side. So that's one document, like the requirements flow down. You see tables for the analysis, like the time estimate, the current time estimates for a particular operation scenarios, the constraint plus the current best estimates. You see the similar things for the powers. Maybe it's a little bit too fast, but you can watch it afterwards. You can change the values, or you will change the value in the client. So now you have a new value, you change the requirement and or design value, the power value and the required value. So that will be saved in the repository. Then on the rich client platform, we will update from the repository into the client. So you see the update happen here, it took the two new values. And then we would run using the Cameo simulation toolkit. So we have a table where we see the values that have changed. Then we would use a tool, which is Cameo simulation toolkit, to execute the model. So it's a SysML model which is fully executable to run a particular analysis according to a particular scenario, which you see here expressed as a sequence diagram, SysML sequence diagram. You get up some plots which show, in this case, the power consumption, two locations, one in the dome and one in the computer room, and the total. And the simulation would record the maximum over time and then verify at the end, which is so very briefly here, against the requirement. It will tell you pass-fail. And then the tables will be automatically updated, and you can publish them again to the document, and the document would have your results of the latest analysis. So what we use for that as an integrating platform is something we call OpenMBE, a model-based engineering environment. The good thing is about that is that we have been able at JPL with some effort to open source almost a complete platform for system engineering. OpenMBE is the integrating part of something bigger, which is OpenCAE, which involves all the ECAD, NCAD, and PLM. Architecture. So we have this, I mentioned these two clients already. Magro is one client. There's another one. We have a third, meanwhile, which is Tom Sawyer, which is an automatic layout, very sophisticated automated layout tool. The model repository addresses the following concerns. So it provides some infrastructure for versioning. So we have element level version control, the workflows, access control, so who can see what, read, write, access, and so on. You can basically put whatever you like, from documents, screenshots, to SysML models, but everything will be represented as a model element in our model, and you can create the relationships. You have some platform, which is the engineering view model platform, on top of which the view editor, for example, is built, but you can build on top other views that you want, not only a document one. And it's a multi-tool and multi-repository integration across the engineering environment. So it integrates system engineering and slowly integrates subsystem engineering tools. So you don't have to read this, in particular in the back end with binoculars, but this gives us an impression of the infrastructure we have. The engineering into the OpenMBE is the one in the red circle. That's a little animation using also an executable model of our OpenMBE. So we have a SysML model, which is also generated and also executes to simulate the different workflows that we have. You would see something like we have Magic Draw on this side, which is the build of the commercial off-the-shelf tool plus our customization for the integration with our model repository, which is generic on this side, the integration with Doors and G, where we have built an integration. We are now at the moment integrating Jira into our repository, so we can combine Jira tickets. We will automatically create a branch. We will be able to track model elements with respect to a certain Jira ticket as an issue tracker. So we're working on all that. Now, I'm very interested. So at the moment we have the system level simulation, which is mostly SysML. But over the last few years, the FMI, the Functional Mockup Interface standard, has been gained a lot of popularity in industry for co-simulation. So you would have the architecture model like SysML as what is the hub, but then you would delegate or outsource all the analysis, particulars analysis, to various tools. It would not be in the SysML model. So at the moment there are like more than 80 tools already supported, which provide an integration with through FMI and SysML. So the Kenya simulation toolkit that we use provides a framework where you can hook in different parts. It's not a closed system, but actually it's an open system where you can add your own simulation platform for analysis tools, and it's widely supported, and it's very, very impressive. So, as a summary, so we have seen that, most of you probably know that they're all over the place, and they are mostly connected through documents, and still a lot of information is only documents, and it's not very well connected with respect to the other information in models or in other documents. We have integration between requirements and the behavioral model and the performance of this design, which we can verify and analyze. We have some method which describes how to construct such an executable model in order to carry out these simulations and analysis. We leverage executability using ESEM, ESEM, co-simulation in the future with FMI, but also co-analysis is supposed to be. Like for example, we have something which is a behavior analysis engine, which is a generic engine which allows you to plug in different analysis tools as well. And then you would be able to, for example, hand over an equation system that comes from the system model and it would solve it for you, or some scheduling. For example, if you want to start up your system and you have some constraints like the maximum power consumption should be this, what's the optimal schedule to start up this motor first with respect to the other motor, or whatever you want to do, and work out the schedule. So that infrastructure we have. We have the automated requirements verification of the architecture, as I showed a little bit before. So you have the requirements in your system model, and you analyze them with the simulation or with some other analysis tools to verify if the conceptual architecturalization meets the requirements. And the documentation we have, like all these 5 documents, are generated all from the model, and the documentation is supposed to be consistent across these documents as long as they're auto-generated. So, thank you very much.
The person in the back.
Just in time.